From a distance, Europa looks almost dead. It is a moon slightly smaller than our own, wrapped in a pale shell of solid ice, sitting at -160 degrees. But if you look closely at those deep reddish-brown scars crisscrossing the surface, you realize something is missing. There are almost no craters. In our solar system, a surface without craters is a surface that is constantly being wiped clean and rebuilt. And that happens here because the ice is floating. Beneath that frozen crust lies a vast ocean of liquid salt water, likely holding twice as much water as every ocean on Earth combined. It stays liquid this far from the sun because Europa is locked in a constant gravitational tug-of-war. Jupiter and its neighboring moons pull on Europa, stretching its interior as it orbits. The moon is constantly being kneaded like dough, generating massive internal friction. That friction produces heat, preventing the dark waters from freezing solid. Life on Earth requires three distinct things: liquid water, energy, and specific chemical ingredients. With its deep salt water, internal heating, and chemical compounds bubbling up from the rock below, Europa is currently the best candidate we have for an ecosystem existing beyond our own planet. Scientists have known about the evidence for this ocean since the late 1990s. So if a world holds this much promise, why did it take until 2024 to finally launch a spacecraft explicitly designed to study it? Because getting there requires surviving an environment that actively destroys metal and silicon. Jupiter has a magnetic field 20,000 times stronger than Earth's. It captures charged particles from the solar wind and accelerates them, trapping them in massive, high-speed radiation belts that completely swallow Europa's orbit. If you want to map Europa, you'd logically park a spacecraft in orbit around it, but an orbiter circling this moon is permanently parked inside that radiation belt. High-energy particles would tear through the computer chips, collision by collision, destroying the flight electronics in a matter of months. To study the ocean, engineers couldn't simply build a standard probe. They had to abandon traditional mission architecture entirely, inventing a machine capable of surviving one of the deadliest places in the solar system. This is Europa Clipper. At roughly $5.2 billion, it is the largest and most expensive spacecraft NASA has ever built for a planetary mission. Every structural choice you see here is a direct physical response to Jupiter's hostility. Survival relies on a specific orbital geometry. Clipper won't orbit Europa. It remains in a wide, elliptical loop around Jupiter, diving inward for 49 high-speed raids above the moon. Afterward, it retreats millions of kilometers into deep space, resting and beaming data back to Earth. But even brief dives require heavy armor. Nearly all of the spacecraft's vital flight computers and instrument electronics are sealed inside a central container called the vault. Its walls are 9 millimeters of solid aluminum-zinc alloy, entirely dedicated to absorbing radiation impacts before they hit the delicate circuits inside. And because they avoided radioactive power sources, the ship has to run on solar energy. Out at Jupiter, sunlight is desperately weak, requiring Clipper to carry massive solar arrays stretching the length of a basketball court. Even fully extended, they'll generate just 600 watts, less power than it takes to boil a domestic kettle. Out of its 6,000 kilograms at launch, only 352 kilograms are scientific instruments. The entire remainder of this enormous structure is devoted strictly to fuel, power, and physical armor. But just months before launch, that armor nearly didn't matter. Engineers learned a specific transistor used throughout their electronics, a MOSFET, was failing at much lower radiation doses than originally promised. These parts were already heavily integrated into the flight computers, and the vault had been bolted shut for months. Opening it up to manually replace thousands of tiny transistors would cost millions of dollars and guarantee they'd miss the narrow alignment of the planets needed for launch. Unable to physically look inside the ship, NASA rapidly convened a team of specialists to pore over circuit diagrams, simulating exactly when and how the spacecraft's functions would fail as the transistors degraded in deep space. What they finally found saved the mission. The transistors were indeed vulnerable, but tests revealed a strange quirk in the silicon. If given enough time away from the intense radiation in slightly warmer temperatures, the silicon parts partially heal themselves. The exact flight path designed years earlier to protect the metal hull of the ship accidentally rescued its defective interior. Those long, looping orbits, stretching out into the safe zone, provide the exact rest periods the failing transistors need to recover before the next dive. On October 14, 2024, Europa Clipper finally managed to leave Earth. But because the spacecraft is so heavily armored, it's too massive for any existing rocket to throw directly to Jupiter. Instead, it has to borrow momentum from the planets themselves. In March 2025, Clipper will skim just 884 kilometers above the surface of Mars. But surprisingly, the goal here isn't to speed up. The gravity of Mars will actually be used to make the spacecraft lose speed. This diagram shows the mechanics at play. By shedding energy, Mars drastically bends the spacecraft's trajectory, dropping it directly back toward Earth in late 2026. Earth's much stronger gravity will then act as a massive slingshot, hurling the heavy ship out toward the edge of the inner solar system. When it arrives 5 years later, it faces the opposite problem. It's moving too fast. Just before firing its engines, it will skim past Ganymede, the solar system's largest moon. Ganymede's gravity will pull backward on Clipper, acting like a planetary parachute to help it safely lock into Jupiter's orbit. This 2.9 billion kilometer journey requires an elaborate exchange of momentum between 3 different planets. Every gravity assist was planned backward from the moment of arrival, ensuring the vault reaches its destination with exactly the right energy. Once it arrives, the real work begins. During each of its 49 rapid passes, Clipper will activate its entire payload of instruments simultaneously. It will fire deep penetrating radar into the crust, measuring exactly how thick the ice is, and searching for the boundary where solid frozen water gives way to the liquid ocean. At the same time, micrometeorites constantly blast tiny grains of Europa's ice into the vacuum of space. The spacecraft will physically fly through these clouds at thousands of kilometers an hour, catching the debris in a specialized dust analyzer, effectively tasting the ocean's chemistry without ever needing to land. But it is crucial to state plainly what this mission actually is. Europa Clipper is not a life detection mission. Out of its 9 state-of-the-art instruments, not a single one of them is capable of identifying a living organism. If something is swimming down there, this spacecraft won't see it. The goal here is chemistry and physics. Clipper will map the ice, measure the salts, and determine if the energy required for biology actually exists in the dark. It is establishing whether the physical ingredients for life are truly there, so that the next multi-billion-dollar mission knows exactly where to drill.